All right, so let's talk about how to simplify radical expressions. So if you have a radical expression like the square root of 12 here, for example, when we ask you to simplify it, we're just asking you to break it down so that whatever's in the square root can't be broken down anymore. So let's talk about how you would break one down. There are a couple different schools of thought on this one. Um, I happen to really like my way of doing it, but I found that a lot of students that I've worked with happen to kind of like the other way of doing it. So I'll show you both. I'm going to show you my way first. Okay. So basically, what you're going to do is you're going to break 12 down into all of its prime factors. To do this, I make what's called a prime factorization tree, which I have just started over here. And what I'm going to do is I'm going to break down 12 into two factors. Give me two things that multiply to make 12. Okay? Some people say 2 and 6. Some people say 3 and 4. You'll see it doesn't really matter in the end. I'm just going to do 2 and 6. And what I'm going to do here for this tree is anytime I get a prime factor, I'm going to circle it. And remember, prime just means that I can't break it down anymore. Okay? 2 can be broken down into factors. It's 2 times 1. But 1 is kind of pointless in this case. Anything multiplied by 1 would be itself. So that's kind of pointless. So 2 is a prime factor. 6 is not prime. I can actually break down 6 further. 6 can be broken down into 2 and 3. And so when we take the square root of 12, what we're really doing is the square root of 2 times 2 times 3. And what you can do here is the square root. Think about this separately for a second. I want you to think about the square root of 2 times 2. Okay? If you have 2 times 2, that's 4. And the square root of 4 is 2. But what I want you to think about here in an abstract sense is if you have anything multiplied by itself under the square root, the result would just be that number outside of the square root. And so that's kind of how I like to think about these. The 2 times 2, the square root of that is just 2, except it's going to be on the outside of the square root. So this will be 2 on the outside, square root, and then there's really not much I can do with the 3 that's left inside the square root. Okay? So the square root of 12, you could break down into 2 times the square root of 3. Now what's interesting is if you go into your calculator and you type in the square root of 12, you'll get a number. If you type in 2 times the square root of 3, you'll get the exact same number. Okay? So that's one way to do it. Another way to do it is people like to break down 12 and try to find the largest perfect square. Okay? And by perfect square, I mean numbers that if you took whole numbers and multiplied them together, it would give you these numbers. So some of the first perfect squares are 1, which is 1 squared, 4, which is 2 squared, 9, which is 3 squared, and you can kind of see where I'm going here. So on and so forth. We could make this list forever, but, for the sake of time, we'll just go out to 100. Okay, so these right here are called perfect squares. And what some people like to do is they like to say, okay, can I break 12 down and get one of these numbers as a factor? And so what they'll do, this is the alternative method, I'll put it in red, not to signify that it's worse, but just that it's different. So what they'll do is they'll say, all right, the square root of 12 happens to be the square root of 4 times 3. Okay, so 4 is a perfect square. And then once you divide by 4, you'd be left with 3. And then what happens from here is they say, okay, if you have the square root and you're multiplying under it, you can actually break it apart and take the square root of each individual thing and multiply that. And so at this point, you have the square root of 4 times the square root of 3. The square root of 4 is just 2. And then you multiply by the square root of 3, so that's just 2 radical 3. Exact same answer in the end. Some people, I don't know about a majority of my students. Maybe it's just because they were taught this the first time they learned it. A lot of my students like this red method. I kind of like this method up here where you find truly any pair inside the radical becomes 1 on the outside. Okay, and by 1, I mean this was a pair of 2s, so you get 1, 2 on the outside. We'll do some more examples here. All right, let's look at another one. So simplify 2 times the square root of 18. So we're just going to leave that 2 out front alone. And so this is going to be equal to 2 times the square root of, if you like my method, the prime factorization, 18. I'm going to break it down into 2 and 9. 2 is prime. 9 is 3 times 3. And 3 is prime. So really what we've got is 2 times 3 times 3 here. And so since there is a pair of 3's here, one of them will come out. When we take them both out, the square root of 3 times 3 is just 3. Because that's what a square root is. It undoes squaring something. Squaring something is when you multiply it by itself. And so if you take the square root of a number multiplied by itself, you would just end up with that number, if you think about it. All right, so this will be 2. And then we're going to multiply by the 3 that came out. And then we're left with the square root of 2. So those 3's, they come out from underneath the radical, and we get 1 on the outside. So if you simplify this, 2 times 3 on the outside is 6, and then radical 2. So this would be your answer. The 2 times the square root of 18 is equivalent to 6 times the square root of 2. If you put them both in the calculator, they would both give you the exact same number. To be fair to the people who like the other method that I showed, if you had 2 radical 18, this would be equal to 2 radical. And then is there any way we could break 18 down so that we would get a perfect square as one of the factors? We can. It would be 2 and 9, actually. So this would be 2 times 9. So this would be 2 times the square root of 2 times the square root of 9. And this would be 2 times the square root of 2 times 3. That 3 is not under the square root, by the way. And so since we have a 2 and a 3 here and everything's getting multiplied together, you can say that that's equal to 6 radical 2. Same answer either way. All right. On this one, let's do simplify the square root of 180. So we're going to take 180, and I'm going to break that down. One of the nice things about these is if they end in a 0, they're divisible by 10. If they end in a 5, they're divisible by 5. Let's see, what other pointers do I have? If the digits themselves, if you add the digits separately and they add up to something that's divisible by 3, then the number itself is divisible by 3, which is really weird and interesting that works out. If the last 2 digits of the number are divisible by 4, so like in this case 80 is divisible by 4. If the last 2 digits are divisible by 4, then the whole number is divisible by 4. You don't have to look at the whole number, you can just look at the last 2 digits on the right there. If something's divisible by 2 and 3, it's divisible by 6, but that's not super helpful. I don't know if there's a trick for 7 or 8 or 9. So, sorry. Maybe there are. I don't know. If you know of one, leave it in the comments section. All right. So 180 is, I'm going to say 10 and 18, and unfortunately neither one of these is prime, so let's start with the 10 and break the 10 down until we get prime numbers. So 10 is 2 and 5. Those are both prime, actually. 18 is 6 and 3. 3 is prime. 6 is 2 and 3. And 2 and 3 are prime. All right, so what is the square root of 180 really? It is the square root of, let's see, 2 times 2 times, so I'm just going to like mark these off here as I do them. All right, 2 times 2. Let's see, there's a couple 3's there. Oh, don't want the highlighter, just want the pen. 3 times 3. So I marked off my 3's. And we still have a 5 in there, so let's write that 5 down. Times 5. Oh, I don't want green, I want white. Times 5. Okay, so now for me, every pair that we have on the inside will become 1 on the outside. So for me, this looks like 2 on the outside times 3 on the outside times the square root of whatever's left on the inside. So we got rid of the 2's and the 3's. So there's only 5 left on the inside. So this would be 2 times 3 is 6 times the square root of 5. That would be your final answer. This is why I like my method more than the second method, because if you try to do the second method, the square root of 180, you know, you start to break this down and you're like, all right, are there any perfect squares that go into this? There are. It's 36 times 5, but I don't think a whole lot of people would realize that 180 is 36 times 5 and break that down into the square root of 36 times the square root of 5 and get 6 radical 5. Maybe you can. I probably have some students in my class who are just going to be stubborn and be like, well, I'm going to do this method anyway, just to prove you wrong. And I'll be like, okay, that's fine. More work for you. All right, 350, the square root of 350. I'm going to break that one down. This one's nice. It's got a 0 on the end of it, so 10 and 35. 10 is 2 and 5. That's always nice and easy. 35 is actually pretty nice. That's 7 and 5. And that is actually, those are both prime. So this is going to be the square root of 2, 5, 5, 7. Did I get everything over there? 2, 5, 5, 7. Yep. We got everything. Cool. So this is going to be, we've got a pair of 5s in there, so we'll get a 5 to come out. So it'll be 5 times the square root of 2 times 7, which is not really much you can do there. So we'll just write 5 square root of 14 there. And we'll be done with that one. And I think we got one more here. All right, let's look at a maybe more difficult one. So 6 times the square root of 7,560. So 7,560. Well, it ends in 0, so it's definitely 10 times 756. 10 is 2 and 5. That's nice. All right, so this ends in a 6, so I know it's even. So I'm going to roll with that too. Let's see. 756 divided by 2 is 378. And that is also divisible by 2. So a lot of times on these, if they're divisible by 2, I will go as long as possible. That would be 189. 2 times 189, is that right? Yep. All right, so 189 looks like it might be divisible by 3. So 9 plus 8 plus 1 gives me 18, which is divisible by 3. So this is divisible by 3. So I'll break that down. 3, and then 189 over 3 is 63. And, ooh, I recognize 63. That is 9 times 7. So I got a 7 there. Make that a little more clear. And then the 9 just happens to be 3 and 3. Okay, so what we've got here is 6 times the square root of, and we're going to make a really long square root. Okay, let's just start out. So how many 2's do we have? We've got 1, 2, 3. So 3 2's. So 2 times 2 times 2. How many? I saw some 3's. How many 3's do we have? 1, 2, 3. So 3 times 3 times 3. What else do we have here? We've got 5 and a 7. So we'll write those down. Times 5 times 7. All right. So we've got a pair of 2's, a pair of 3's, and that's the only thing that's going to come out. So this will be 6 times 2 times 3. What's left on the inside after we knock out those 2's and 3's? We've still got a 2, a 3, a 5, and a 7. So 6 times 2 times 3 is going to be 36. And then the square root of, unfortunately, there are no pairs in here, so we can't really break this down. So 2 times 3 is 6, times 5 is 30, times 7 is 210. So there you go. If you ever wanted to know, apparently 6 times the square root of 7,560 is equivalent to 36 times the square root of 210. If you don't believe me, throw it in your calculator and try it. But I bet it'll work.